Hi everybody, this is your introductory video on the interval of convergence. This video is going to be all the intro stuff you're going to need. In class is whenever we're actually going to derive a new series, and I'll show you how to actually find the interval. This is all the stuff you're going to need to know ahead of time in order to do what we're going to do in class. So what we've been doing the past week and a half is learning all the necessary tests for convergence. There's about 7 or 8 of them, and you have to know them, know how to use them, know how the conclusion works. Recall that before we did that, we did a bunch of series stuff. So we started with series, we jumped to convergence. Now we're going to go back to the main topic. The whole point of convergence was to do it with series. So we're going to go back to Power and Taylor series and use all our knowledge of convergence to find the interval of convergence. Now, we've found intervals of convergence before whenever we first started talking about geometric sequences and series. And one of the first power series that we derived was this guy. We did long division. So if you go to the beginning of your notes of series, you'll see this. We found that it was this series here. And more generally, we could write it like this, or I should say equals here. That's better. So this is the summation notation, and this is the general term, our generator A sub n. And if we wrote it as P sub n of x, our polynomial of nth degree would be all these terms going up to x to the nth power. So this is a polynomial approximation. We did a bunch of stuff with polynomial approximations. And we know that as we add more and more terms to our polynomial will approximate f better, and it will lay on the function closer. Now, if we look at this series right here, to go from one term to the next, you multiply by x. So this is clearly going to be a geometric series with a common ratio of r. So this is geometric here. And we've already talked about, again, how for a geometric series, in order to converge, the ratio must be less than 1. In this case, the ratio is x. So I'm going to say x is less than 1, which you can write out and make it look more like an interval like that. So we're combining all the stuff we've already talked about, series, convergence, geometric series, common ratio, and we're going to combine all of it to talk about the interval of convergence. So let me show you this visual, which I've shown you before. And in red here, I have 1 over 1 minus x. That's our function. This is our polynomial right here, up to the bth term. So in purple here, I have my polynomial approximation. We're going to watch it get closer and closer to our function as we add more terms here, because I have a slider for the number of terms. Also, what I've graphed here is -1 and 1. These here are going to be our interval of convergence that we saw right there, because I want you to visually see what the interval of convergence is going to look like. So if I hit play here, as I add more terms, first of all, our polynomial gets very, very close to our function, but it only gets very, very close to it within this interval. It'll never get close to it here. It'll never get close to it here. So the interval of convergence, you have to be within these x values to get a good approximation. Anything outside is going to be a horrible approximation, especially over here. Now, I also want you to look at the endpoints here. The endpoints are going to be a huge deal when we do the interval of convergence. Sometimes it will convert, or the polynomial will converge to the series at the endpoints, and sometimes it won't. And it's going to be your job to test it. So you'll use your test for convergence to find that. Notice that at the the endpoint of 1, there's an asymptote there. So our series will never converge for 1. At -1, it might reach the actual function. We're not really sure if it converges at this endpoint unless we did some math, which I'll save for Monday. So again, testing the endpoints, sometimes they work, sometimes they don't. Sometimes they do different things, like 1 will work and 1 won't. So in class, we'll do a lot of stuff with that. So where were we here? So make sure you have that copy down, pause if needed. We're going to go to the next chunk of notes here. So again, our polynomial does a good job approximating our function on this interval, or you can write it like that. That interval is called the interval of convergence. It's where the polynomial is very close to the function. Now in class, again, if you're following along with your earlier notes, we did functions like this, this, and this, which are slight variations of this. And we use substitution to write out those new series with very little work to be done. And we saw that this has the interval of convergence like that. And we got the new intervals of convergence for these series by messing around with this here. So we took the common ratio R and set it less than 1. That's what you're always going to do here. You'll find the ratio, set it less than 1, because the ratio has to be less than 1 to converge. So I'm going to do these real quick here. If you look at your notes, you saw that we wrote this out here, and we could see the common ratio from term to term, or you can compare to the general geometric sequence or series form and know that this is your common ratio. So my common ratio here is equal to x cubed. So you take your ratio, you set it less than 1. Solve for x, do the cube root of each side. Cube root of 1 is 1. So the the interval of convergence didn't change there. Here, my common ratio is 2x squared. So I'm going to take my ratio and set it less than 1. Solve for x. X squared is less than a half, and x is less than 1 over the square root of 2. So if you want to write it more like an interval, it was like that. So this is very similar to what we're going to be doing with intervals of convergence. It's just there's going to be a little more involved than just this. And here we saw that the ratio is negative 2x, so I set it less than 1. The negative doesn't really matter, and I divide each side by 2, and I get that. So that's what we've already done, but realize that these are geometric series, so I can just say, oh, okay, R is equal to this, set it less than 1. So it's based on the common ratio R. But there's a lot of series, like any other series except for a geometric series, they don't have a common ratio R because R is changing. But then we've talked about for the ratio test, what happens to the ratio as n gets really, really big, like goes to infinity. We could write our ratio like this. And then we would see, does that ratio approach a value that is less than 1? So then at some point it would converge if that was true. So this was the ratio test, and we're actually going to do the ratio test to find the interval of convergence. So the ratio test is going to be basically all we use to get the interval of convergence, and then to test the endpoints, we use the other test. So we will find the limit of our changing ratio, see if the ratio levels off or approaches something less than 1. So that's what we're going to be doing. You use the ratio test to find the interval of convergence because our Taylor series will not have a common ratio. So the last thing I want you to do is to write down or draw this little visual here, which will help you understand how the interval of convergence versus the radius of convergence works. So let's say we're on our x-axis here and we have our function and we have our series, which is approximating it. We will be finding what's called the interval of convergence. And let's say it's this right here, interval of convergence. And we're going to be testing our endpoints here and here. So whenever we find the interval of convergence, the endpoints may or may not converge. That will be your job to test. And in fact, it might seem like extra stuff that doesn't matter, but on free responses, the way they test your knowledge of convergence is pretty much always with the interval of convergence, and the endpoints will be about 1 or 2 of the 9 points. So they're a pretty big deal. In the interval of convergence, the interval of convergence is symmetric about the series center. So that means, let's say the center is right here. Then we have this thing called the radius of convergence. The radius of convergence will be half of the interval of convergence. So starting from the center, moving out to the end of the interval of convergence, that's your radius of convergence. It's basically how wide it is from the center. And the radius of convergence is always going to be some value r. As soon as you get outside of your interval of convergence, you get divergence. And sorry, this is kind of messy here. Divergence. So again, the two main terms you need to know here are the radius of convergence, which is from the center to the edge, and the interval of convergence. The interval of convergence is twice the radius of convergence, kind of like the diameter is twice the radius. So within the interval of convergence, these are the x values where we can get sensible values out of the infinite series. Anything outside isn't close. All right, so make sure you have all this written down. In class, we'll be actually doing interval of convergence. I haven't really shown you a whole example here. I'll save that for in class. We will be doing the ratio test to find the interval of convergence, and then we'll be testing our endpoints. All right? So make sure you have all this written down, and I will see you Monday.